Okay, some of you were complaining that my voice is hard to hear on the back. I'm a silent speaker, so if you have trouble hearing me, make some sign. You can just make, I don't know, just so that I will speak louder. Questions? On Monday, we defined this concept of the electric field. And basically, it's the force felt by a point charge. We made several definitions. And the electric field can be defined as the force that the charge feels divided by the charge itself. Of course, this is the electric field at a given point. So the charge is placed at the point P. This is the charge we have at the point P. Or let's show it by the vector R. This is the electric field at a given point is given by the force that a charge placed at that point feels divided by the charge itself. And then we looked at, for the point charge, let's say if you have a point charge over here, the electric field created by that point charge is 1 over 4 pi epsilon 0. Well, let me use the capital Q over here. Times capital Q over R squared in the radial direction. If the Q is a positive charge, it is pointing away from the charge. If it's a negative charge, the electric field will be pointing towards the charge. And then we studied the continuous charge distributions. Well, we started studying them. So we had this infinitely long wire problem with a linear charge density lambda. Lambda is just the charge per unit length. If you take some length L, if that length has a charge Q, then lambda is just this Q over L. And then we had calculated and shown that the electric field magnitude was given by 1 over 4 pi epsilon 0. 1 over epsilon 0 Q over 2 pi R. Again, it was pointing, if the charge is positive, the electric field is pointing away from the wire. Okay, one thing you should note is this R is the distance of the point from the wire. This is our R. This is the distance from the wire, so it doesn't matter whether you are looking at this point or some other point at the same distance from the wire. Those 2 points have essentially the same electric field. Now, any questions on electric field? Well, both will be considered correct. But I would advise you to write with epsilon 0. Okay, now let's continue along these continuous charges. Well, one problem we will study is we had this infinite wire. You can also imagine an infinite surface. So you have a conducting plane. You put some charge on it, the charge will be distributed around. So you have an infinite plane with uniform charge density. Now, if you remember what we did in the case of an infinite wire, okay, the infinite wire is not a point charge, so we cannot directly use the Coulomb's law. And in fact, the end result has a completely different form, has a somewhat different form than what we have for the electric field in the Coulomb law, because the Coulomb law is essentially valid only for point charges. For this infinite wire is not a point charge, so we cannot use it directly in that form. But what we did was we divided this wire into very small segments, and then each one of these segments was very small. So we can approximate them to be a point charge. So we calculated the electric field created by each one of these almost point charges at this point. We summed them up using the superposition principle of the electric field, and eventually we took the limit that this length goes to actually 0, so that we obtain the electric field of an infinite wire. In the case of an infinite plane, we will also do basically the same thing. But rather than taking such infinite, very thin things, very small segments, for this infinite wire, infinite plane, the first thing we will do is we will just divide it into very small rings. Still, these rings are not point charges, but each ring, if you open it up, it's basically a wire. So just like in the example of the wire, we can divide each one of these rings into very small segments. Now, each one of these very small segments is almost a point. Eventually, we will take the limit that the thickness of each one of these rings goes to 0, and the length of each one of this segment goes to 0. In that limit, each one of these squares becomes an actual point. So now the Coulomb law will be exactly valid. And just like in the case of the infinite wire, we just calculated the electric field of each one of these separately and then summed them up. We will do basically the same thing over here. But rather than attacking this problem straight away, let's start with the simpler one. Just a ring. Assume we have a ring. A uniformly charged ring. Let's say it has a total charge Q and a radius R. So we have this ring whose radius is R and has a total charge Q. And for simplicity, we will just be looking at the electric field, let's say at this point. So we take the center, imagine a line passing through the center perpendicular to the plane of the ring, and take a point on that line at a distance, let's say, d from the center. So this will be the problem we will address first. Now, just like in the case of the wire, I will first divide it into very small segments. And let's assume each segment has a length dl. D meaning that it will be very small. Eventually, we will be taking the limit that that length goes to 0. Now, that segment that I'm looking at will have a charge, let's say d small q. Well, the total charge is q. It's uniformly distributed. So the charge of any segment will be proportional to the length of that segment, or the fraction of that segment to the total circumference. So this is the fraction of the length of the segment to the circumference. Since charge is uniformly distributed, the total charge in that length will be the charge multiplied by the fraction of that length compared to the full circumference. Or you can say that q over 2 pi r, this is the circumference. This is the linear charge density of the ring. So if you multiply it by the length, you get the charge of the segment. Now, to calculate the electric field, both the direction and the magnitude, you can imagine this straight line from that segment to the point we are interested in. Just for the purpose of the sketch, I will assume that Q is positive. So the electric field will be pointing in this direction. The electric field created by that segment dl. Let me call it dE. And the magnitude of this electric field, it will be 1 over 4 pi epsilon 0 times dq over the distance of that point from my charge. What is that squared? The distance squared. What is the distance squared? D squared plus r squared. So basically here I have a right triangle. One side has a length r, the radius of the ring. The other side has the length d. So the hypotenuse squared is just the sum of the squares. And the direction is given by that. Now again, to write it in a vectorial form, we have to take the horizontal, the x component and the y component. We have to deal with them separately. So the electric field created will be 1 over 4 pi epsilon 0 dq over d squared plus r squared. This is the total magnitude. To calculate the horizontal component, just multiply with the cosine of that angle. Cosine theta in the I direction plus 1 over 4 pi epsilon 0, the same magnitude. To calculate the vertical component, just multiply it by the sine of that angle. The next task is just to sum over all these segments. That would give me the total electric field. Now I will take a shortcut. You see, there is this segment over there. Just diametrically on the opposite side, there is another segment. And that segment will create an additional electric field in this direction. It will have exactly the same magnitude because that segment will have the same length as this one. It is at the same distance from that point as this one, but it's just pointing upward with the same angle theta. So when I sum these vectors, the vertical components, one is pointing up, the other one is pointing down. When I sum them up, it will just give me 0. So the only thing left is the horizontal component. So I will not write down the vertical component. I know that it is already 0. It will be 0 when I sum all the contributions. The only non-zero contribution will be from this term. So the horizontal contribution will be 1 over 4 pi epsilon 0 dq over d squared plus r squared. What is cosine theta, by the way? Theta is this angle also. What is cosine theta? Well, it's an angle of this right triangle. The adjacent side has a length d. The hypotenuse has the square root of this sum. So that is the cosine theta. D over d squared plus r squared to the power 3/2 in the I direction, or 1/2, plus the vertical component, which will sum to give me zeros. That's why I don't write it explicitly. Now the total electric field will be just the sum of these terms. dq divided by d squared plus r squared to the power 1/2 d in the I direction. Now this sum is over the various segments on the ring. So if I go from one segment to the other segment, does this term change? It doesn't change. Does d change? It also doesn't change. R, it's the radius of the ring. It's independent of which segment I'm looking at. This is also a constant. So everything here is constant. I can just take them out of this summation sign. This is equal to 1 over 4 pi epsilon 0, d over d squared plus r squared. This is the 3/2 to the power 3/2 times sum over d cubed in the I direction. Well, dq is the charge of one of the segments. I am summing all the charges of the segments, but that would give me just the total charge of the ring. This is just the total charge. One over 4 pi epsilon 0, q times d divided by d squared plus r squared to the power 3/2 in the I direction. This is the electric field created by the ring on a point along the line passing through its center. Let's see if our answer makes sense. Now, there are several limits that we can easily check. If d is equal to 0, our answer predicts that the electric field should be 0. Now, if you go back to our initial sketch, does it make sense that when d is equal to 0, the electric field should be 0?
Yes.
Why?
When you're at the center of the ring, there is an equal electric field coming from all tiny segments of the ring, and they cancel each other out.
Yeah, basically, there are symmetrical segments. The electric field from this segment and the electric field from this segment, they are pointing exactly in opposite directions, and they have the same magnitude, so they just cancel. So that limit makes sense. So that is one limit we could check. When d is equal to 0, our answer makes sense. The other limit we can look at is what happens when r is equal to 0, when the radius of the ring goes to 0. What do you expect the answer to be? So when the radius of the ring goes to 0, what do you expect the answer? It will be just a point charge. So we should recover the Gauss law for point charges. Well, let's see if it works. When r is equal to 0, this term is absent. So we have the d squared. We have to take the power to the power 3/2. That gives me d cubed. Well, there is a d over there, cancels one of the factors in d cubed, so we have the q over d squared. But that is what the Gauss law predicts. This factor is identical to the Gauss law. Here we have a 1 over d cubed, and the I hat vector is just the direction away from my point charge in that limit. So again, in that limit, my answer makes sense. So it's likely to be correct. Now, any questions in this derivation? Once we are done with this, now we can attack the problem of an infinite plane. Questions? So now uniformly charged infinite plane. So this will be my plane. Let's say the side view of my plane. So I will be, this is not a wire, a plane. So I'm looking at the electric field at this point, at a distance, let's say L, from the plane. Now the top view of this, well, just assume all the sides go to infinity. I am right above this point. So the top figure is, I look just from the side, this is my plane. And this bottom view is, I look right from the top. Now, as I mentioned before, what we will do is I will just imagine this infinite plane to be a collection of many rings. Now let me just pick up one of the rings, an arbitrary one. Let me pick up this one. Well, let me name its radius to be r. It has some thickness. Let me call the thickness to be dr. And let me also call the surface charge density to be sigma. So we define the surface charge density similar to the linear charge density. So you just imagine some area. And if that area has a total charge Q, then sigma is just Q over A. And since it is a uniform, by saying that it's a uniformly distributed charge distribution, what we are saying is that whatever area you imagine, whatever shape it can have, whatever position it can have, this ratio is always the same. Now, for this ring, to write down the electric field of this ring only, what we need? Well, 1 over 4 pi epsilon 0 is just a constant. We need to write down the total charge of the ring. And the radius, we had called it now small r. The only thing we need is how to write the charge. So what is the charge of the ring? Well, you see, since it's a uniform surface charge density, if you imagine any area, the charge within that area will be just the area times the surface charge density. So what I need to write down is, what is the area of this ring? Well, the ring, it's very thin. I can imagine opening it up. If I open it up, it just becomes a rectangle with a height dr. So dq is just sigma times dA. And dA, the area of the ring, is dr. This is the height of the ring, the width of the ring, sorry. If I open it up, it just becomes this rectangle. And the height of the rectangle is dr. The width of the rectangle is just the circumference of this ring. And the circumference is just 2 pi r. This is the area of my ring. Well, of course, this is exact only in the limit as dr goes to 0. Only in that limit it becomes exactly a rectangle. The area is exactly given by this. But eventually, since we will be taking the limit as dr goes to 0, I ignore the possible errors. They will just vanish. So now I know the charge of the ring. Then I can write the electric field created by that red ring. This will be 1 over 4 pi epsilon 0. The charge is sigma times 2 pi r times dr. This is the charge. Let's see what else we have. I had already written down the charge of the ring, that is q. The d, in the previous problem, we had defined the d as the distance of my point from the center of the ring. In this problem, I had defined that distance to be L. So here I multiply this with L, divided by L squared plus R squared to the power 3/2. In the I direction, this is the electric field created by that red ring only. Now the next thing is I just need to sum all these. The total electric field will be the sum of 1 over 4 pi epsilon 0 times 2 pi r dr sigma L over L squared plus R squared in the I direction. Well, in the limit as dr goes to 0, I have basically infinitely many terms over there. So that becomes an integral. 1 over, well, let me make some simplifications. This just becomes 2. 1 over 2 epsilon 0. I have sigma times L. Here there is the 3/2 power. R times dr over L squared plus R squared to the power 3/2 in the I direction. What are the limits of R? I have to put some limits to evaluate this integral. Well, what I did was, if you go from ring to ring, dr is essentially the change in the radius of the rings. I'm summing over all these rings. dr, it is at the same time both the thickness of each one of these rings, it is also the change in the radius of the rings as I go from ring to ring. And I define it to be positive. When I'm summing over all these rings, I'm actually summing over all possible values of r. Because I start from r is equal to 0, that is the innermost ring. I go up to r is equal to infinity, that is the ring at the infinity. So that gives me the limits. So I start from 0 and go up to infinity. This is the electric field. Now let's calculate this integral. So how do you propose that we evaluate this integral? Suggestions? Well, let's try. U is equal to L squared plus R squared. du is equal to 2R dr. So the electric field becomes sigma L over 2 epsilon 0. I had, well, R times dr is du over 2 divided by u to the power 3/2. The limits, well, when r is equal to 0, u is L squared, u is L squared. When r goes to infinity, u becomes infinite. Well, this becomes sigma L over 4 epsilon 0 I in the horizontal direction, or in this case in the vertical direction, that is away from my plane. I have the integral of u to the power 1 over u to the power 3/2 is minus 2 over u to the power 1/2. If you take the derivative of this one, it just becomes minus 1 because it's 1 over. So if you increase the 1 over 2 by 1, it just becomes 3/2, but you also have a factor 1 over 2 that cancels this 2. And u goes from 0, u goes from L squared up to infinity. So this is equal to sigma L over 4 epsilon 0 I times, when u is infinite, it's just 0, 1 over infinite, minus, there's another minus sign from here that makes it a plus 2 over, when u is equal to L, square root of u is, when u is L squared, the square root of u is just L. So these L's cancel, and we end up having the electric field is equal to sigma over 2 epsilon 0 times I. So for example, the electric field doesn't depend on L. Whether you are, if this is your infinite plane, the electric field at this point, if the surface charge density is positive, it will be pointing away from the plane, and it will have a magnitude sigma over 2 epsilon 0. If you are looking at the electric field at this point, again, it will be pointing in the same direction with a magnitude exactly the same. So it doesn't matter whether you are very close to the plane or away from it, you have exactly the same electric field. Any questions on this derivation? Yes, questions? Okay, where did I lose you? You see, our strategy is always the same. Divide and conquer, in a sense. You have like these extended objects, like the ring. We just divide it into point-like objects. But if it's a collection of point-like objects, then we can just write down, use the Coulomb's law. So in this derivation, here is the Coulomb law. It's just the overall coefficient times the charge creating the electric field divided by the distance from the electric field squared. This is just the Coulomb law. The next thing was, okay, electric field, although this is the magnitude, it's a vector, so we have to take into account its various components separately. So what we did over here is we just decomposed this electric field into the horizontal and vertical components. Now this is the horizontal component, just multiply the magnitude by the cosine of theta. This is the vertical component, multiply the magnitude by the sine of theta. And now we made an observation. We said that, okay, there is this segment over here, we are calculating the electric field of that segment, but there is another segment over here, diametrically opposite. But this segment will create an electric field of the same magnitude, but just pointing upward rather than downward. It will have exactly the same horizontal component, but the vertical component will come with a minus sign because it's pointing upward. And when I sum them up, when I sum the two, the vertical components will cancel, the horizontal components will just add. So for every segment I can imagine, there is a diametrically opposite symmetrical another segment. When I sum these two segments, the vertical components cancel, the horizontal components add. So this observation told me that when I sum the contribution of all the segments, I only have the horizontal segment, not the vertical component, because they will add up to be 0. That is why I just ignored this part. If I ignore it, the next thing I said, okay, cosine theta, I define this angle to be theta, but you see, for all these segments, that theta angle is the same. It doesn't change. As I'm moving all around this ring, it doesn't change because I am on this line, on the line passing through the center. That is why it doesn't change. If I were on this at this point, let's say, neither this argument that the horizontal components will cancel will hold, nor the argument that theta is a constant will hold. Only because I am along this line, that theta angle is 0 and the vertical components cancel. Now, theta is the same for all the segments, and the cosine of theta is just given by this length. There I have this right triangle. That's my right triangle. This is nothing but the radius of the ring. This is my distance from the center, which is given to be d. So the hypotenuse is just d, the radius squared plus d squared. The cosine of this angle in this right triangle is the adjacent side divided by the horizontal, the hypotenuse. So it's over here. This is the cosine of the angle. Here I didn't write the vertical part because when I sum, I already said that it will be cancelled. Then I'm doing the actual summation. The total electric field will be just the sum of the electric field, the contributions to the electric field from each one of those segments. So there is this term. I have to sum over all such contributions. Plus, I don't write this anymore because I know that that sum is exactly 0. That's why there I put the dots, but here I don't have the dots because they gave me 0, that sum. Now, in this sum, I can just take the common factors to each one of the terms, the factors that do not change from segment to segment. So this is out. This factor, d over d squared plus r squared, is out. And then what is left inside is just a summation over dq's. dq is the charge of each one of the segments. And when I'm summing over all the segments, I sum the charges of each one of the segments, I get the total charge. And the total charge of the ring was given to be capital Q. And then I am done. This is my electric field. The electric field is in the I direction. You see, in this example, the I direction is the horizontal direction. But the horizontal direction is the direction along this line pointing away from my ring. That is the crucial thing. You see, if I rotate my ring, nothing should change. If I rotate the ring, the electric field will not be in the horizontal direction anymore, but still it will be along this line pointing away from the ring if Q is positive. If Q is negative, it will be pointing towards the ring. Now, any questions on this ring example? Because in the next part, I will be using that ring example. Then I'll go to the other problem. An infinite plane. That is the side view. Just imagine the surface of this table. I am looking at the electric field at this point. What is the electric field over there? There is a uniformly distributed charge density on the surface, which means that given any area on the surface, if you calculate the total charge on that area, this Q over A is a constant. It's the same no matter which area you choose, no matter which position you choose, you place your area at. So sigma being Q over A is just a constant. Or you can also interpret this as if you have an area, the charge inside that area is just the surface charge density multiplied by the area independent of the size, shape, and the position of the area. That is what is meant by uniform. Then we said, okay, I have this infinite plane. I can divide my infinite plane into rings. So I have a very small ring, then a bit larger, then a bit larger, then a bit larger, 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 so that when I add up all the rings, I get an infinite conducting plane, uniform charge with uniform charge density. Since the charges, if I add the charges of the rings, I get this infinite plane with a uniform surface charge density. When I add the electric fields of the rings, I should also get the electric field of a uniform infinitely charged plane, conducting plane. So then what I did, I divided into rings. I had already calculated the electric field of one ring. And that was this expression over here. Okay, that was the expression for the ring. And I just used this relation. Well, 1 over 4 pi epsilon 0 is just the same. Here, keep in mind this capital Q is the charge of the ring. Now, in my example, what is the charge of the ring? Well, the ring has an area, dA, given by this 2 pi r times dr. And so the total charge of the ring is just its area multiplied by the surface charge density. So it's sigma times 2 pi r times dr. This is the charge of the ring, which corresponds to this q over here. And then I have this d, in my previous example, was the distance of the point at which I'm evaluating the electric field from the center of the ring. Now in this problem, I am defining that distance to be L. Now the directions, in the case of the ring, the direction was in the I direction, which was nothing but the direction along the line passing through the center and my point. And it is pointing away from my ring. Well, you see, in this direction, in this case, my ring is in the plane, so the I direction is this one in this sketch. And in this sketch, the ring is over here. So the I direction is pointing upward. So this is the electric field created by one of those very thin rings. Then the next thing is the plane is just the sum of the rings. So the electric field created by the plane will be also the sum of the electric fields created by the rings. So I have to take this expression and sum over all the rings. And as I said, eventually I will assume that the rings are infinitesimally thin. So basically I have infinitely many rings. And that summation has the special name of an integral. So this summation is just nothing but this integral over here, with all the factors of epsilons, pi's, etc. And then the rest is basically calculus to evaluation of that integral. Now you can, in fact, instead of the infinite plane, you can ask what is the electric field of a disk. The derivation will be identical. The only difference being, instead of going up to infinity, you will go up to some finite radius r. That will be give you a disk instead of the infinite plane.
I could not set the DI.
Which dA? Okay, so let's go over that. This is my ring. Now you are looking from the side. This is my ring. Now what I do is I just cut my ring and open it up. I just open this up. What you will get if you open it up it just becomes this shape. Do you agree? Well, this will be the shape. Now, what is the height of this thing? Well, just the thickness of the ring. This is dr. So this length is nothing but the circumference. This is 2 pi r. So this area is the same as this area. Basically, they are the same thing. So that area is just, it's just a rectangle. 2 pi r times dr, the product of the sides. This is my dA. Just multiply by the surface charge density, you get the total charge.
Can
minus?
Sure, electric charges can be both positive or negative.
Then the direction of the electric field will change.
Well, you see, this expression is correct independent of the sign of the charges. But of course, you are right. In this sketch, I am drawing these electric field lines as if sigma is positive, as if I have a positive charge distribution on the surface. If sigma was negative, you see, then basically I'm multiplying this vector. This vector is always pointing in this direction. That is the I direction in this problem. This is always true. But if sigma is negative, a negative number multiplied by a vector is a vector pointing in the opposite direction. So if sigma is negative, then the electric field vectors will be pointing towards the plate. Questions?
Why doesn't the electric field depend on the distance L? Is it because it's an infinite plane?
Well, it's basically because it's an infinite plane, as you said.
So if we had a finite plane, it will depend on L.
True. In fact, let's just write down what the expression would be. The electric field of a disk well, you have, in this problem, you have the disk with the radius, let's call capital R, and it has a total charge Q. So the surface charge density is just Q over pi R squared. The charge divided by the total area, if the charge is uniformly distributed. We are assuming that the charge is uniformly distributed, so this is the uniform surface charge density. The previous derivation is identical, except the limits. So this was the electric field in the case of an infinite plane. And by the way, I am looking for the electric field at this point, at a distance L. So again, I'm taking the center of the disk. I'm taking a point along this line passing through the center perpendicular to the disk. Now, the only difference between this problem and the infinite plane problem will be the largest ring. In the case of the infinite plane, there is no largest ring. Their radius can go up to infinity. In this problem, the largest ring will have the radius equal to the radius of the disk. So this will be the electric field. Now let's go back. We had already evaluated that integral. The upper limit is just capital R. So this becomes sigma L over 2 epsilon 0 in the I direction. So this is R squared plus L squared this time. 1 over L minus 1 over R squared plus L squared under the square root. This will be the final answer. So you see, the result now does depend on L. Well, let me simplify it slightly. This is equal to sigma L over 2, no, there's no L. Sigma over 2 epsilon 0 of, in the I direction, 1 minus 1 over square root of R over L squared plus 1. So that now, for example, in the limit as r goes to infinity, this term just becomes 0, and we recover our previous result. And, well, let me also replace the sigma. In a sense, you can think of it also like this. Let's imagine you are looking at this infinite plane. Is there a way that you can determine your distance from the plane by just looking at it? Well, if you are very close to the plane, what you will see is just a plane going infinitely far away. If you are at this distance. If you are at this distance, again, it will be just covering all your one side of your view. Nothing will change. Well, if you have a finite object, let's say there is this table. When I look at this table from this distance, it just covers such an angle. If I go further away, it will cover a smaller and smaller angle. So my view will change, and hence the electric field naturally changes. In this infinite objects, independent of your distance from the object, your view will not change. Everything will look the same. So that's mainly why the electric field in this problem doesn't change as you move away from the plane. This argument doesn't work in the case of infinite wire, though. Okay, let's give a 10-minute break, and then we will continue.